Good morning, everyone. My name is Aurèle Adam. I'm a researcher and teacher at the optics group at the Applied Physics faculty. And today, as a last Design Engineering for Fysici course, we would like to ask you to do a little experiment at home where you will have to design and calibrate and work with what we call a spectrometer. And the question we will ask you is it an LED? Is it an LED? The Achtergrond is the spectrography, and I will guide you through the history of spectroscopy in the next minutes to make you understanding how today is related to what happened exactly 400 years ago. So the topic I want to talk to you here is spectroscopy, and the whole journey starts in 1672 and will bring us to today, you in your room, where you will have to start this depth. What happened at that time in 1672? Well, actually in 1665 already, there has been a large plague running in London and in UK. This plague had actually a bad thing happening for a lot of people. They had to go to confine themselves. And one person especially was actually studying at the Trinity College, Cambridge at that time. And he had unfortunately to go home and to spend almost more than a year at home waiting for the plague to go by and to go to his manor, Walthorpe Manor actually, for more than a year. And this person, you probably know him very well, is one of the most famous scientists of all the time. It's Newton. Newton exactly had the same problem than you have. He had to study at home. But what did he do? Well, did he just open books and do courses like you did? Well, actually, at that time, internet wasn't existing, so he had to find another things. He had to occupy himself. And actually, he did a great thing. What he did, for example, during that time, he actually looked at light. He was a bit bored, and he started to make experiments at home. And here, I give you the recording that he wrote in 71 in the Philosophical Transaction of Royal Society of actually what he did during this plague time. It's in Old English, of course, but you can read it around. So as you see depicted in the picture here, what Newton did is he puts the curtain and the curtain in front of the window, opened a little hole and let the light of the sun going out. And he placed a little prism, so a prism at the entrance. And he understood already that the light would be refracted, as we all know already for 100 years from the Snell's-Descartes law at that time. But what he found out is that actually the white light of the sun was giving you, through the prism, an oblong form of colors. And he was, as you see it, a pleasing divertissement. So he found it very funny. But then, of course, he started to wonder why. Why suddenly you get colors when you put light through a prism from the sun? And he started to actually analyze that and try to understand. And as you all know, by the first course we did together on MGO, you know that we have been working on the dispersion of light in medium. And this is what you can explain again from the courses. If you remember, I show you here a depiction of what's going on. You have a beam of light going through the prism. Part of the light is refracted inside the prism and then getting out again. But here what's happening is, because of the dispersion of the glass, that means the index of refraction of the glass is not constant for all wavelengths, suddenly the angle of deviation, what we call d here, will be depending on the incident I angle, but also in the index. Therefore, the light will get out differently for different colors. And as you see, we see a beautiful rainbow coming up from this white light source here in the prism. And this is what Newton has been studying hardly during his time at home, but of course he did also calculus during that time and discovered many other things about light. But here we'll focus about this discovery, because what he did was analyzing light and analyzing actually the wavelengths of the light. That's the first time that someone really looked at it and understood that the white light was made of many colors. And the colors that we thought were in fact coming up by themselves, they are initially in the sunlight or in the candlelight, and it's just there hidden for us, but you can with a prism start to see them. And that's not really the birth of the spectroscopy, but the first things that people say, hey, now we can use a prism to study these colors. The next step was actually a person that you may also know, William Herschel. It's a bit later, as you see, it's like 100 years later. and this is actually the first experiment we could say about really spectroscopy, is that he discovered that there is also light we don't see. So he did the same experiment than Newton. He's actually even referring to Newton in that. And then explaining, okay, I did the same than Newton. I take my prism, I put the colors, but then I do something extra. I put a thermometer at the end of the rainbow. And what he could figure out is that even he doesn't see any light there, he could see that the thermometer was changing the temperature reading. It was getting warmer. So strangely, he doesn't see anything with his own eyes, but he sees an effect by the fact that you have the light, which is there above the red color. That's what we will call actually the infrared. And as we know, infrared is related to heat, and therefore that's what actually Herschel has been measuring. But the beauty of it is that it's for the first time, he also drew the plots on the right here on the presentation, which is the study of the spectrum of the light. And that's the beauty of it, is that he started to really look at the spectrum, the analysis of all the different wavelengths, and to even make a plot and to try to figure out what was the intensity of every of these colors. And this is a plot that you've seen. It's a beautiful plot, but this is not yet done in a complicated way for the experimental part, because the idea was just to use a prism, and there is not really a lot of work on the experimental part, on the object itself, on the setup itself. But that was more the measure that was interesting here. The next step came actually very quickly 2 years later by Wollaston. Wollaston was also a very famous scientist that invented many optical elements, but he was very famous for actually building his first spectrometer. So to really have a device that was made to study that automatically, for not just only looking at the sun light, but actually getting the sun getting through an object and then looking at the color response, the spectrum from this object they put inside. So if you put glass, or if you put a coated glass, or if you put a colored object, what the light goes through, you don't see the same color. And this is where Wollaston started to understand that actually the colors are not generated by the object, is that they are just partially absorbed, and therefore we see the resulting colors going through the object. And again, very lovely setups that he has been building, and very sharply later he was able to have such a good spectrum from his setup, from his spectrometer, that he could start to see dark lines in the spectrum of the sun. As you can see on the right slide here, what you see here is the composition of the light of the sun, but you see that you have dark dots there. That's not what you usually clearly see on the rainbow, for example, but that's what you will see if you start to study and have a very good setup to see what's going on with the sunlight. He could not really understand that at the beginning, but really quickly people started to wonder, like, maybe there is actually something between us and the sun, like all the atmosphere and the different layers that actually are absorbing some of the light, and therefore they are not visible anymore, these colors. And there started the whole business of spectra of chemical elements. And again, it's very quickly afterwards, 40, 50 years later, people started to really study carefully all analysis of chemicals and figured out that all these chemicals are actually absorbing, as this gas, for example, are absorbing the colors, and therefore have a very narrow spectrum lines present in the spectrum that you measure when the light goes through this object. On the left, you can see one of the example of such a spectrometer. And on the right, the classical result you will have if you have a gas going through, like the atmosphere going through, that is in between the light source and your detector, and the different lines you can see. So this is really the start of understanding that you can actually now not just look at the sun, but also study physically chemical compounds. You can also see properties of materials using the light, and therefore starting to understand what this is made of. And of course, I'm jumping very quickly to something very recent, which is the project from the European Space Agency, the ESA, called Tropomi, which is actually a Dutch satellite which costs around 220 million, has been launched in 2017. This is actually a very good spectrometer in a satellite, and this is to observe the Earth. So now instead of looking at the sun, what we are actually doing is looking down to the Earth and making map of the Earth. But what kind of map are we doing with this? Well, let's see how first it works. So it's a pretty complex spectrometer. It's not only just one color spectrum is looking at many colors spectrum. We'll see. You recognize again in the center image the famous idea to decompose through a prism the different colors. Here it's a bit more complicated. It's a prism with also a grating, and the grating also disperses nicely the light, so you have an effect of two kinds. First, the refraction of the prism that changes with the index of refraction, but also the fact that you have different facets there that also change a bit the direction of the light. What you see as a result is in the end of the man, the different colors from, for example, a light source, which should be white, and the actual instrument placed on the base on the top-down window. So, as I said, it's a bit more complicated. You don't have just one continuous spectrum. You actually can measure 3 different types of bands. They are called bands, and they are much scattered compared to the previous system that tropomy has been replacing. So you have the low bands in the low wavelengths, which is more or less the UV band. Then you have a band around 700 to 800 nanometer, and then you have a high band in terms of wavelengths, which is in the infrared 2.1 micrometer. And looking at these different bands, which are especially there to monitor specific lines of gas, we can follow and monitor the ozone content, the methane content, the formaldehyde, and the aerosol and carbon monoxide, NO2 and SO2 contained in the atmosphere. And the beauty of this instrument is that it's much better also in terms of resolution than the previous satellite that has been sent, and is able to give a complete map of the Earth in one day. It's a huge amount of data that is collecting per day, but that means every day is make a full map of the Earth with all these different monitoring all these different contents, which are all possibly toxic to human, and that can follow nicely the evolution of pollution. And that comes back to today. As you know, we are in most of the Europe locked down, not totally in Netherlands, but in other countries things have stopped. People don't go to work, they stay at home, and therefore there's much less pollution created by human. Factories stopped, cars stopped, and therefore these different compounds that are produced by humans due to mainly fossil fuel actually disappear. And this is what I want to show you here. This is a very recent map, March 2019, I think it's like 3 days ago. They analyze what is a classical map content of nitrogen dioxide in the north of Italy during the period in 2019 and 2020. It's a movie, so you will see over the days how from December to March things are changing. And as you can see, in 2019 the concentration is more or less constant, but then in 2020, as soon as the lockdown started, actually the concentration diminished tremendously. And that's bringing me back to you and to what you have to do for depth. In this case, what I want and what we want with the team is to realize that staying at home, as Newton did, was actually not a bad thing. And he could actually discover many things. And we want you to redo this in a sense. We want to turn you to impersonate Newton and to be home and to try to figure out how you could, with whatever you have around, build a spectrometer and looking at what kind of lamp you have at home and figure out, are they LEDs? Are they incandescent light? Or are they something else that maybe you never guess what it could be? I think Rolf will explain you better how we will do this with what you can have at home. But please keep up the good work and realizing that sometimes being in a room locked in can actually give you ideas to do crazy stuff that can bring you good scientific results. Thank you for listening, and I wish you good luck with this project. Thank you.